Alright, welcome students to the lecture number 6 where we will be discussing the band structure as we find from the Kronig Penney model. So I think the Kronig Penney model we have discussed in the last class, but let me do a few brief recap of this. So as you know, this is a very idealized, very simplistic model to describe the periodic potential for a one-dimensional solid, right? So idea is that once you understand the one-dimensional solid, we can generalize it for the three-dimensional case, and then we try to understand the behavior of electrons in presence of this periodic potential. Okay, so I am now discussing describing these two this potential consisting of two regions, region 1 and region 2, and the wave function for the electrons in the two regions are given by psi 1 and psi 2, right? And so as I discussed in the last class, the periodicity of the potential is A plus B. A is the distance between two atoms, let's say, right, and B is the width of the potential, so the periodicity is A plus B. Now once you know the wave function, once you define the wave function, then you write the Schrodinger equation. So you basically solve the Schrodinger equation for electrons in the two regions, right? So let me write for region 1. Region 1 there is potential is 0, right, within 0 to A. So therefore the Schrodinger equation is minus h square by twice m d2 psi 1 dx square equal to E psi 1, right, for x between 0 to A. Right, and for region 2, this is the other case, right, where you include in addition to the kinetic energy, now the potential energy V naught psi 2 equal to E psi 2, where E is the total energy of the electrons. Right. So now to simplify this, you consider alpha square equal to 2me by h square, right. So you see that in the second equation for psi 1, right. So you consider alpha square equal to 2me by h square, and for the first equation you consider beta square equal to 2m h by h square and b0 minus e, that is beta square, right. So these two parameters alpha square and beta square, once you put in equation number 3 and 2, then you will get the equation which we will solve, right. So now before that we have to consider the solution of this for this wave function, which will be of the form of this psi x equal to e to the power I kx times ukx, where ukx has the periodicity of the lattice, right. So this is called Bloch function. So what Felix Bloch has shown actually is that that if the wave function of an electron which experiences the periodicity of the potential, experiences periodic potential in a solid, must be given by this e to the power I kx, right, times a periodic function ukx, which is the periodicity of the lattice, right. So there's the Bloch function. So that means if an electron within a lattice experiences the periodic potential, I mean if it moves through this periodic potential, right, so its wave function will be given by the Bloch function. So that is a major realization of Felix Bloch to solve the problem or to find out the behavior of electrons in presence of solids in presence of periodic potential. Okay, so so this is the Bloch function, right, and therefore these electrons in solids with in presence of potential, these are also called Bloch electrons sometimes, or sometimes also called band electrons. I will come to that later. Okay, so that means this is the wave function. Bloch function satisfies Schrodinger equation for perfect periodicity of lattice. Okay, so that is the condition. So if there is a periodicity of the lattice, then the wave function has to be given by the Bloch function. Okay, So now with this, with the Bloch function, then you put this Bloch function in the in these equations, in the equation 2 and 3, right, and then with this you get these two equations. So in terms of u1 and u2, right. So so these equations are d2 u1 dx square plus twice ik du1 dx plus alpha square minus k square into e1 equal to 0, right. Similarly, you have the equation for the region minus b to 0, that means where the potential is finite potential, which is v0 within the region minus b to 0. Alright, so now you have these equations. So and then you know the solutions of these equations. These are given by this e1 and u2 equal to this, right. So e1 is a e to the power I alpha minus kx plus b e to the power minus I alpha plus kx, right, and this is u2 given by c into this exponential term and d into this exponential term, right. So now one has to solve these equations, right. So to find this equation, I mean to solve this equation, you need to find out these constants, right. So to determine these constants, we use this periodicity and the continuity of these wave functions, right. So that means so now let us consider this this periodic potential here, which Kronig Penney has assumed, right. So wave function has to be continuous, right. So that all of you know. So therefore u1 at x equal to 0 must be equal to u2 at x equal to 0. So that means the wave function at x equal to 0, that means this is in region 1, so that is on the right of 0 line, right, must be equal to the wave function. So u2 at x equal to 0. So u2 at x equal to 0 is on the left side of the 0 line, right. So this has to be continuous, and therefore also the derivative must be continuous. So du1 dx at x equal to 0 must be equal to du2 dx at x equal to 0, right. So this is the condition for the continuity of the wave functions, right, and also the wave function has to be periodic. So therefore u1 at a x equal to a must be equal to u2 at x equal to minus b, right. So in the minus b region the wave function is u2, and similarly for the derivative also this is valid, so must be valid. So du1 dx at x equal to a must be equal to du2 dx at x equal to minus b, right. So once you write this, then you determine the energy, right. So we are interested in determining the energy of the states. So ultimately what we are trying to look for is the relation between energy versus k, right. So you remember in free electron case, energy is equal to h square k square by twice m, right. So it's a parabolic function, right. However, in this is not a free electron case, right. So here you have introduced the periodic potential. So we are interested to find out what happens to the energy, what is the relation between the energy and the wave vector in this case, right. So now now to solve these equations u1 for u1 and u2, right. So these equations, solution of these equations will be given by the case where the determinant of these coefficients a, b, c and d must be equal to 0, right. So if you do a little bit of algebra here, and so which I am skipping here, so I write the equation that we get, right. So this is the equation. So beta square minus alpha square by twice alpha beta sine of hyperbolic beta b times sine alpha a plus cos hyperbolic beta b times cos alpha a equal to cos of k into a plus b. So if you remember, alpha is the energy term basically, right. So we have defined alpha square as equal to twice m e square twice me by h cross square, right. So that is what we have defined as alpha. Now, to solve this, the Kronig Penney has simplified further. So they have assumed that this potential, the height of the potential is infinite. So they have considered kind of a delta function, the barrier as a delta function. So where potential is infinite, whereas B, the width of the potential, tends to 0, right. However, B naught, the product of V naught and B must be finite, so must be non-zero value. Okay. So further simplification, Kronig and Penney have used, they considered that let us say the B0 is infinite kind of a delta function, and B0 B which is the width of the potential, tends to 0. So however, but B0 times B is non-zero, is finite. Okay. So with this condition, so if you put these conditions here in equation 9, then you get this simplified equation, right, which is P sin alpha by alpha A plus cos alpha A equal to cos K A. Now, what is P? P we are defining as m V0 B divided by h cut square alpha, right. So, so this is P. So what we see here is that the left hand side is a function of alpha A. What is alpha? Alpha is the energy term, and on the right hand side this is cos of Ka. So it's a function of K. There is the wave vector. There is the wave vector, right. So therefore we are getting now the relation between energy and the wave vector, right. And P is this factor, P factor, that is the strength of the binding energy of the electrons, because this is the, so the higher, the larger the V0 value, right, higher is the binding, stronger is the binding of the electron to that lattice point or to that particular atom. Okay. So at that particular location simply. So and if P tends to 0, so that means you can consider that V0 maybe will be nearly equal to 0, right. So in that case, so that is very weak binding. So in that case, alpha will be equal to K from equation 10, right. Okay. All right. So now we have this equation now to solve, right, E versus K. So how to solve this equation now? So this equation doesn't have an analytical solution. So what they have tried is a graphical solution, right. So what you do in a graphical solution, basically you plot the left hand side and the right hand side separately and see which are the common points. These are basically the common points are the roots of this equation. So now you consider the left hand side, which is a function of alpha A. Now first term is sin alpha A by alpha A, and when alpha A is nearly 0, so we will limit that alpha A is 0, your sin alpha A by alpha A becomes 1, right. So therefore at alpha A is 0, the left hand side is 1 plus P, right, which is the maximum value for this. So they have considered for this function for P equal to 3 pi by 2, right, and then they have plotted this this equation, right. So plotted this function P sin alpha A by alpha A plus cos alpha A, right, which is an oscillatory function, as you see. And what you also see, so please focus on the red curve here, right. So I am talking about the red curve, which is the left hand side function, which is an oscillatory function. So what you see here, this curve actually crosses -1 in the right, and on the right side this curve crosses this -1 line at pi, right, and similarly +1 at for alpha A equal to 2 pi, again -1 for alpha A equal to 3 pi, and so on, similarly on the left hand side also. Okay, so what is minus 1 plus 1? Now alpha a, now you see that cos of alpha a or has a maximum value of plus minus 1, right. So what we do is on the right hand side cosine of Ka, so we plot the maximum values of cosine of Ka, right. So that will be again plus minus 1. So if you plot these plus minus 1 values, so these are basically two lines. Now this curve, red curve, which falls within this plus minus 1 and 1 lines, right. So that means those are the points, those are the values which are allowed, right, which are the roots of this equation. Those who lie outside plus minus 1, so plus minus 1 is given by the right hand side, right, the oscillatory function is given by the left hand side. So any part of this oscillatory curve which falls beyond this plus minus 1 line are not the is not a solution of this this equation number 11. So now considering this, what you see here is that there is an allowed band of the energy. So what is x axis now? This is important to note. X axis is the energy axis, right. So as you move along the x axis, you are actually increasing moving along the higher energy states, right. So because alpha is an energy term, alpha square equal to 2m square by h cross square, right. So 2me by h cross square. So therefore alpha is the energy term. So that means as you go towards the right hand side from 0 line, right. So you are moving along higher energy states. So now if you look at this, so you see that that this red curve which lies within this plus minus 1 line, right. So this part can be considered as the as a band of energy. Okay, so and this I am showing by this rectangular green rectangle, right. So this is the part which is the solution, for this equation, equation number 11. So therefore these are the allowed values, right. So therefore these allowed values are actually form bands, right. So these are number of energy states within this within this green curve, green rectangle. Similarly, if you move along, then once you cross plus pi, right, so then you get this forbidden region. So that means those are the this is the region where this red curve crosses plus minus 1 line, right, beyond plus pi. Now again when it enters within minus 1 region, right, so then it again moves into the allowed states. So therefore what we see is that from this equation, roots of this equation shows that there are some allowed and forbidden energy bands, right. So you have alternatively green and white are the forbidden range, right, because here the curve goes out of this minus 1 plus 1 line, and as I said minus 1 plus 1 is the maximum values of cos of Ka, right. So therefore as you move along the energy along the higher energy side, you see that this you get energy bands, both allowed and forbidden bands. So two allowed bands are separated by forbidden bands, right. So this is, so what you find from the Kronig Penney model is that the energy spectrum, right, energy spectrum has both allowed and forbidden bands. And the other interesting point is that we see that the width of the allowed energy band increases continuously as we move towards the higher energy side. So right, so that's what I am writing, width of the allowed energy band increases with energy along the x axis. Okay, so now this is what we see. Now you remember, let me now pause and try to recollect what we knew for the free electron case, right. So that means where the electrons do not see any potential, right, potential is 0. In that case, energy versus K values, right. So these are some discrete values but these are continuously moving, right, towards the higher energy states, right. So, discrete values corresponding to the allowed k values, right. So, for if you remember, corresponding to each k values there is a corresponding energy state, right, which can accommodate 2 electrons in that case. But these are continuously moving because E versus k is a parabola in that case, right. Whereas here you see that if once you switch on the periodic potential, right, you see that the energy state is not continuous now, energy is not continuous anymore. So, the spectrum has both allowed and forbidden bands, and what you also see that as you move along the higher energy axis, right. So, you see that you find the energy bands are continuously larger, energy bandwidths are continuously larger, right. Now let us consider what is the effect of P on the energy spectrum. Now, what is P? P, if you remember, P we have defined as mv0 Ba by h square. So, and that is the strength, that is the measure of the strength of the binding energy. Okay, so that's what P is. Now, what happens if P is 0? So, as I mentioned also in the last slide, that if P is 0, so that means B not equal to 0. So, that means this energy becomes continuous and it kinds of a free electron case, right. So, now let me show you this curve. This is this I have taken from the original paper of Kronig and Penney, which was written in 1930s. Alright, so the scan copy of this is what I am showing here, right. So, in the x axis this is P, right. So, they have plotted as P by 4 pi on the left side of this blue line and 4 pi by P on the right side of the blue line. So, this is essentially the same thing. So, the leftmost point is actually P tends to 0, right, and the rightmost point is the P tends to infinity. So, what happens, what you see here is that P tends to 0 is the case where it is a free electron like case, right. So, therefore, energy versus k, so it has there is no gap in the energy, right. So, it is continuously number of states corresponding to each allowed k values, right. But now, once you switch on, you start seeing these bands of energy. Therefore, on the left side, right hand side, so if you go towards the higher P value, towards P tends to infinity, you see that the bandwidths there is an energy band. However, once P starts becoming very large and large, right. So, your actually what happens is, so that means the electrons become more bound, right. So, P tends to infinity means it is a high binding energy, very strong binding energy. So, that means electrons are not actually moving through this crystal. So, they are bound within this to this potential, and therefore, this becomes like a particle electrons within a box potential, and therefore, the states becomes discrete states again. So, therefore, you see that at P tends to infinity you do not see any band anymore. So, this becomes kind of a discrete state. Okay. So, the shaded area is the allowed band. So, this is the effect of P. So, when from P tends to 0 to P tends to infinity, what is the effect of these P values? That is the measure of the binding energy. What is the effect of this on the energy spectrum, right. So, once we understand that, right, so then we know that we now find the dispersion relation. There is a relation between E versus K for electrons which experience some periodic potential within the lattice, right. Okay. So, this is the dispersion relation. Now, what you see in the dispersion relation is that there are in the E versus K diagram, right. So, there is a discontinuity at K equal to n pi by A, right. So, that means at pi by A, twice pi by A, thrice pi by A, there is a discontinuity in the energy versus K. So, that is what we have just discussed and just shown in the last slide. So, this now, so that means there are certain K values up to which these energies are allowed, right. Beyond that, at certain k value, so k equal to pi by a or k a equal to pi, right. So, there is a discontinuity. You have seen that from that graphical picture, right. So, if I go back and look at this, so yeah, so you see that, so there is a discontinuity at pi by a, right, when alpha p tends to be small, alpha will be equal to k. So, therefore, at k values, so you have discontinuities at pi by a, for example. Now, so these energy regions within this allowed values of pi k equal to pi by a, these are defined as Brillouin zones, as certain zones, and these are called Brillouin zones, right. And so these are defined as the zone within first or second discontinuity, right. So, let me elaborate this further. Now, let us say, now from those whatever we have studied, let me show you a E versus k diagram, how it looks like here. So, x axis is the k, right. So, this is again one dimensional case, y axis is the E axis, energy axis. Alright. So, if you plot this, now you see, as you have seen, that there is an allowed a band, and between two allowed bands there is a forbidden band, right. So, that means at pi by a we have seen that there is a discontinuity, right. So, there is a certain number of certain width of the band is forbidden. So, that means what it means essentially is that electrons in this solid can't have any energy within this forbidden energy state, okay, within this forbidden energy band, I mean. Okay. So, electrons can have energy. So, electrons can exist with energies within this energy band, allowed energy bands. So, now, we can say we talk about first band, second band, etc. Right. So, now, within the region between minus pi by a to pi by a. So, this is this zone, this allowed zone, this is called Brillouin zone, and this is the first discontinuity. So, therefore, this is also called first Brillouin zone. Right. So, similarly, second Brillouin zone starts again from this pi by a to 2 pi by a, right. Similarly, on the other side. So, the second Brillouin zone is split into two parts, right. So, pi by a to 2 pi by a and minus pi by a to minus 2 pi by a. So, this is called second Brillouin zone, and similarly, the other one is called third Brillouin zone. So, let me define it here, right. So, first Brillouin zone 1, Brillouin zone 2, zone 3, etc. Okay. So, now, why do I classify them as these Brillouin zones? So, let me discuss this to understand that, right. So, what we see here is that k is a periodic function, energy is a periodic function of k in this case. So, why is it so? So, on the right side of that equation, you remember, so this alpha a, sin alpha a by alpha a plus cos alpha a equal to cos k a. So, on the right side, this is cos k a. Now, if you put k plus 2 pi a by a, 2 pi by a times n, right, on the right side, then this does not change anything, right. So, right, because cos in term does not change anything. So, it becomes again cos k a, right. So, therefore, these k values are not very discrete values, sorry, no unique values, right. So, that means corresponding to any k value within this within any energy band, right. So, there you can have another k values with the same energy, right. So, and this so these say k values corresponding to the same energy will be given by the difference between these two k values will be given by 2 pi by a times n, right. So, that means all k values, so because it is periodic, energy is constant, energy is the same for this region. So, therefore, all k values can be limited to actually minus pi by a to plus pi by a. Okay. So, that means k within minus pi by a to plus pi by a, all the k values, because these are periodic. So, you can always bring them to there. So, let me elaborate this further. So, this is what I show. I am showing an extended zone scheme. So, that means I have defined Brillouin zone 1, 2, 3, etc. So, let us concentrate on the left side of the figure. Sorry, left side of the slide, right? That is the left figure. So, you know that you see that the first Brillouin zone and second Brillouin zone, as I said, this is split, right? So, now what I meant here is that the second energy versus k diagram in the second Brillouin zone, this can be brought to the zone first Brillouin zone in the left hand side, because the difference between the k values will be 2 pi by a, right. So, if you remember, any values of k which is periodic in 2 pi by a, right, it will have the same energy. Okay, so, this is what I am trying to show here. So, this line solid line in the zone 2 can be converted to is the same as the dashed line in zone 1, right, on the left side. So, I am showing it by an arrow. Similarly, on the left side, so minus pi by a to 2 pi by a, this zone can be brought back to the first zone again. Okay, so, similarly, the curve in the third Brillouin zone, right, can be brought back to the first Brillouin zone on the right side, right, because again the difference is 2 pi by a. Okay. So, therefore, this entire this is called extended zone scheme, right. So, all the zones you show them separately. Now, this can be simplified, this can be shown in a simplified way as I show it on the right hand side, right. So, that is the reduced zone scheme. Now, we call it reduced zone scheme, and where we are plotting the first Brillouin zone, second Brillouin zone. Now, I am plotting it within the first Brillouin zone, third Brillouin zone, I am again putting it back to the first Brillouin zone as I showed here on the left hand side. So, these are all equivalent. So, this is called on the right hand side, what you show here is that the entire band structure that you show only in the first Brillouin zone, and this is called reduced zone scheme. So, all the information corresponding to this corresponding to the behavior of the electrons, right, is there in the reduced zone scheme itself. Okay. So, therefore, it is much simpler. So, you should always draws the reduced zone scheme, but you should understand that. I hope that this is clear by now. So, now let me compare this. So, once you understand this band structure, right. So, what we are seeing here is that if you have electrons, right, which experience this periodic potential, right. So, then what we see is that electrons can have energy bands, allowed band and forbidden band. And so, now let me try to compare this band electrons band structure with respect to the free electron case. I mean, so we are comparing basically the dispersion relation between the relation of electrons in the free electron case and in the band electron case. So, this blue line, blue curve, right, on the left hand side is remember. So, these are again all one dimensional. For simplicity, we are discussing the one dimensional case, right. So, blue dotted line is the free electron case, right. So, E is equal to h square k square by 2i7, it's a perfect parabola. The red one is actually the for the band electrons, right. So, the band is opening up at the zone boundary, first zone, right, pi by a, and then the second zone is also shown. You remember, in addition to this discontinuity, the other feature is that the energy curve at the zone boundary is flattened. Okay. Right. So, you see that deviation from this parabola, so it is flattened at the zone boundary. Okay. For both the case, I mean, for the first Brillouin zone and second Brillouin zone, you see that, right. So, now on the right hand side, I show it in the reduced zone scheme, right. So, both for free electron case and for the band electron case, right. I hope that this is clear for you now. For the free electron case, there is no gap, so it just starts from the point it is where it ends, right. And yeah. So, this is the behavior of the electrons when you consider the periodicity of the potential. Okay. So, okay, all right. So, now once you understand this, now what you see is that there is a band structure, you have both allowed bands and forbidden bands, right. Now, let us try to find out what is the number of possible states per band. So, let us consider the lowest band. Okay. So, we know that this is periodic, wave function has to be periodic. So, L is the length, we are considering the one dimensional length case, right. So, so it has to be periodic. So, this is e to the power I k x plus L times e k x plus L, it must be equal to u on the right side, what is on the right hand side, right. And u k, this is a Bloch function, right. So, u k is the periodic function. So, u k x plus L equal to u k x. Okay. Now, considering these, you have these values k allowed values k equal to 2 pi by n, 2 pi n by L values where n equal to plus minus 1, plus minus 2, etc. Right, and this you get from the boundary conditions. So, now I am trying to show here is that there is in this one dimensional case. Now, this is the k space, right. So, we have discussed actually in the next chapter reciprocal space. So, this is a k space in one dimension, right, and each point is basically one allowed k value. So, what we see is that within 2 pi by a there is only one allowed k value. So, so now what is the number of possible states? That means number of possible k values in the range of delta k will be given by 2 pi by L, sorry, L by 2 pi times delta k, right, because within 2 pi by L there is only one state. So, therefore, number of states given in the range delta k will be given by L by 2 pi into delta k, right. Now, let us try to find out delta k. So, as you know that this k is limited for the lowest band, say. So, k is limited by the discontinuity, right. So, that means k delta k, maximum of delta k can be minus pi by a to plus pi by a. So, that means delta k is 2 pi by a, right. So, this is the maximum. So, therefore, total number of states in this range will be for the lowest band we are considering right now. So, L by 2 pi, right, times delta k. So, delta k is 2 pi by a. Okay. So, that is equal to L by a. So, what is L by a? Let us say if you have n equal to number of unit cells, right. So, we are considering one dimensional case here, but if n is the total number of primitive unit cell in this one dimensional solid, right. So, total length of this solid L will be equal to n times a, right. So, that or n will be equal to L by a, right. I hope this is clear. So, therefore, total number of states in this in this range of k will be equal to n, because we are getting L by a, right. So, total number of states in this range is n, all right. So, therefore, each state can accommodate 2 electrons, and therefore, total number of electrons per band will be twice n, right. Total number of states is n per band, and total number of electrons will be 2n. Okay. So, where n is the primitive unit cell. So, I think this much is for today. All right. So, what we have done here, we have solved this equation, right. So, we have considered a few assumptions. One major assumption is that the potential which we have considered, or Kronig Penney has considered as periodic. Now, he has solved this further by considering this this potential as a delta function, right. So, with this delta function, assumption of delta function, and the width of the function, width of this potential very small. However, the product of the height and the width is with finite. So, they have found a simplified equation with which is a function of alpha a on the right hand side, and on the left hand side, and function of k a on the right hand side. So, we solve this graphically. From graphical solutions, we see that there is a this energy spectrum consists of energy bands, right, which are allowed and the forbidden bands, right. So, each alternate allowed bands are actually separated by these forbidden bands. We also see that as you increase the energy, the bandwidth increases continuously, right. So, this is one thing that we have done, and then we have found out, we have discussed about the role of this the strength of the binding energy, which is P, right, which we see that that if P is very strong, if P is very strong, that means the electrons are strongly bound to the nucleus, and therefore the energy becomes discrete, right, for very strong bindings energy case. Right. So, once we have done that, we have now calculated actually the number of electrons that can be accommodated in one band, let us say the lowest band in this case, which is equal to the twice the number of the primitive unit cell in this one dimensional lattice. Okay, so with this I would like to end this recording for this class 6, right. In case there is any question, please feel free to get back to me. I will be very happy to discuss with you further and take a doubt session, all right. Okay, thank you very much. Okay, bye.